So this is the second lecture of mine on signals and systems. In this lecture 2, I am going to discuss about vectors and signals again, orthogonal vector space and orthogonal functional space or signal space, and how to approximate the signals in this orthogonal vector space or signal space. This is what I am going to discuss today. Let us come to the orthogonal vector space. Here, first I am considering a three-dimensional vector space described by rectangular coordinates. Because it is a three-dimensional, I have x-axis here out of the screen, and towards the right I have the y-axis, and towards the top I have the z-axis. There are three axes here, rectangular coordinate, Cartesian coordinate system, and I am defining three unit vectors, one along x-axis, another along y-axis, another along z-axis. Okay, so ax, ay, az. These are the unit vectors along the three orthogonal axes of a Cartesian coordinate system. Now I am considering any vector, an arbitrary vector A, which is drawn from the origin of the coordinate system to the point A. The point A has the coordinates x0, y0 and z0. So these are the coordinates here, and this is the vector formed to this point. It is called a position vector basically, and the coordinates are shown here. This is x0 is the coordinate on the x-axis, y0 is the coordinate on the y-axis, and z0 is the coordinate on the z-axis. So we already know that. So this vector, any vector, arbitrary vector, can be expressed as the summation of the three components. That is, this is the unit vector, Ax is unit vector, and I have x0 is the coordinate. So this is the scaling factor along the x-axis. This is the quantity basically, x0 into ax, whereas ax is a unit vector along x-axis. Similarly, I have the y0 ay plus z0 az. These are the three components put together. I call it as a vector. So this vector, arbitrary vector capital A, is formed from three components along the three orthogonal axes in the coordinate system. Okay, so these axes are orthogonal to each other. So if you take the cross terms, ax dot ay, it is 0, ay dot az, az dot ax. These are the cross terms, the product, the scalar product of the these unit vectors, they are all zeros. And ax dot ax, so it is the length of the vector basically. So because it is a unit vector, I have length 1 here, and similarly ay dot ay and az dot az, they are also equal to unity. So this is what is the description of this coordinate system. Now, three coordinate axes are sufficient to express any arbitrary vector A in real world space. Okay, if you take real world, the three coordinates are sufficient. Thus, they form a complete set. That's why these three axes can be called as a complete set of functions or vectors here. So, complete set of vectors, and they are called the basis vectors. So, you can express any vector, A or B or C, any vector as the summation of these basis vectors, basically. So, when I take the dimensionality, a straight line, if I take a straight line, it is one-dimensional space. If I take a table surface, it is a two-dimensional space. If I take a real object, it forms the three-dimensional space. So these are the, in the order of increasing dimensionality, these are examples for that. Now, let us consider an n-dimensional vector space. N-dimensional vector space means we are extending the previous three-dimensional access to n dimensions, n dimension coordinate system. But it is very hard and it is impossible for you to visualize these fourth axis onwards. Okay, up to 3 axis we can easily visualize because we are accustomed to that real world objects which have already 3 dimensions, and 4th dimension onwards it is only in terms of mathematical framework you can discuss, but you cannot visualize physically that coordinate system. But however, we require at several phases of data processing or signal processing, we require the n-dimensional vector space. So here, let us consider an arbitrary n-dimensional vector A. So here we are extending the vector. Previously it was x0, y0, z0, x0, y0, z0. Here, okay, a0, x0, y0, z0. So here, because x, y, z alphabets are completed, there are no alphabets left over to use. So that is the reason we switch over the notation from x, y, z axis to x1 axis, x2 axis, x3 axis, xn axis. That is xn axis. So this is basically the n-dimensional space. Okay. So here I am calling this a small n here, and I can say that this is also small n. Okay. So this is what I have: A equal to C1x1 plus C2x2 plus C3x3. This is up to 3 dimensions. And extending to n dimensions, I have Cn plus xn term. Cn xn term. So these are the n components. So you are dividing this arbitrary vector. You are dividing the arbitrary vector as n number of components. Okay, basically n number of components. So here also, I think, a capital N, wherever you have the capital N, you can take it as small n here also. So this is what the arbitrary vector A of n dimensions, small n dimensions, can be represented as the sum of products like this, sum of all components along the all orthogonal axis basically. So here x1 xn, x1 x2 xn are mutually orthogonal and form a complete set. That means no other set is, no other basis function, no other axis is needed to express any vector in n dimensions. Okay, so these are sufficient. These n number of axes are sufficient to represent. So if you take the cross terms, this is what m equal to, m is not equal to n, xm dot xn, the dot products, the scalar products of 2 unit vectors from different axes. That is, m is not equal to n. Okay, x1, x2, x2, x3, x4, x1, like that, any axis, 2 different axes, if I take the dot product equal to 0, and if I take the same thing, that is same axis, if I take m equal to n, in that case it is the length of the vector in that direction. So it is nothing but unit vector, so I will get 1 here. So this is what the equation 1, equation 1 is here and equation 2 is here. So let us continue with the next equations. So what I am doing here is, I am taking the dot product on both sides of equation 1. See, this is the equation 1. Both sides, I take the dot product with xr. xr means r is some dimension between 1 and n. 1, 2, 3, etc., up to n axes are there. And I am taking in the middle, randomly, some axis I am taking, that is nothing but rth axis. The axis r I am taking. So that is the vector along the rth axis is, the unit vector along the rth axis is xr. So I am taking the product, the dot product of the given vector, arbitrary vector, with the unit vector along the rth axis. So that is, this is the left hand side. Right hand side is equation 1, C1, x1, xr, C2, x2, xr. Like that, I have the another term that is CR, XR, XR. Then CN, XN, XR. So like that I have. And in this one, if I take the cross terms X1 dot XR, dot product of X1 and XR is 0. Basically, this term is 0. Similarly, this term is also 0. But this term it is 1 and this term it is 0. So, except this term, all other terms will become zeros because of the orthogonal property of this n-1 axis. Because orth axis have taken out the remaining n-1 axis. If I consider the all dot products will become 0. So this is so LHS left hand side equal to right hand side only single term, and I can, because the length of the unit vector XR is equal to unity, I get CR. It is the coefficient. Basically, it is the how much fraction or how much part of XR is embedded within the vector A. Okay, how much part of XR, how much part of XR component, orth axis component is contained in the given vector A. So that is the meaning of that one. Now, if I rearrange terms, this fraction CR equal to A dot XR. See, this is what is AR XR, and divided by this one, XR dot XR. This is the unit vector. Okay, this is unit vector by value. So this is the, already we have done the similar thing previously. So here also, in case of n-dimensional space also, we have the same thing. CR equal to dot product of given vector with the axis considered, whatever axis you use, XR, it can be something else also. See, you can consider kth also. You can consider pth axis also, like that. Okay. So here I am taking CR, means orth axis. Dot product of A with XR divided by length of that vector. Okay. So that is what I have here. Now let us come to the approximation part. So far, what we have done was, we have described a three-dimensional vector space and n-dimensional vector space also. Three-dimensional vector space, n-dimensional vector space, and both are orthogonal spaces. Orthogonal vector spaces means any arbitrary vector in this can be represented as the sum of three products. That is the three components along the three orthogonal axis. Okay. Similarly, in case of n-dimension, any arbitrary vector can be expressed as the sum of n components, each component lying along the individual orthogonal axis. Okay, that is what we have done. Now, how to deal with the approximations? We require the approximation. So, we have one vector. We want to represent that vector in terms of another vector. So, that is what is approximation. Why we require this kind of approximation is, in signals and systems also, we are going to approximate the signals in terms of some other signals, in terms of basis vectors or basis functions or basis signals. So that is what we are going to do. So to understand that more effectively, we have to first discuss about the approximation of a vector in terms of another vector. So here, this diagram already you are familiar with, and in this, I have one vector F, another vector X, respectively along Y and X axis, and I am projecting this vector F onto the X axis. That means Cx. C is a scalar multiplied by the vector X. So it is a fraction. What fraction of X is approximately equal to the vector F in terms of length? That is what we are seeing here. Okay. So I can say that I am approximating. For example, if I take F, see, this is vector, correct? So this is the first vector, Cx is one vector, and E is another vector. So this vector plus this vector, these two vectors. So first vector Cx plus C, Cx plus E is equal to your first vector, that is F. Okay, Cx plus E equal to F. So this is what is approximation. What is that approximation? This is error. This is the error, and this is the actual approximation is this. So I can say that if I say F, I can also write like this. F is approximately equal to, S is approximately equal to Cx. Okay. This is approximately equal to Cx. And plus error. If you add the error also, I will get the vector F. So I can express the error term like this. E equal to F minus Cx. This is the error vector. This is a vector basically. Okay. Error vector. This is also a vector because see here, E is there. It is a vector here. Okay. So there is this much difference is there. Vectorially, this much difference is there between the two vectors. One is original vector F, other one is approximation of F. I can also call it as, and other way is F cap. I can call as Cx. Okay, Cx. So this is what I have done. If I put F cap, automatically I am approximating the thing. So let me write this again. Okay. So this is what F cap. Now if I take error equal to F minus F cap, approximation of this. In general, we use the for approximation, a cap is attached to the letter so that it is an it denotes the approximation of that, of the actual function or actual vector here. Okay. So this is what we have about the approximation. Now, in the same spirit, I want to approximate a signal in terms of another signal. So here signal, or I can say function, and first I consider the real signals, real functions. So there is a function f of t here. F is a function which is changing with time. F is a function, F is a function as a function of independent variable t. This is what is, I can call this as a function, or I can also call it as signal. It doesn't matter. In terms of another real signal, x of t. So f of t is one signal, x of t is another signal. It is like a, what is the difference here? When I compare to the vectors, in vectors there are no t parameter. So here there is a independent variable x because the f value is changing with respect to t, x value is changing with respect to t. I call it as f as a function of t, x as a function of t. That is the only difference between the vectors and functions and their notations. And over the interval t1 to t2. And here the interval has come into picture because it is varying with time. And in earlier case, in case of vectors, there was no time parameter, there was no time interval involved there. T1 to T2, that kind of time interval was not there. So the same analogy, I have the first function is approximately equal to the c times the second function. So it is the approximation basically. And again, as I defined, it is true only between the intervals T1 and T2. Outside the interval T1 and T2, that is when t equal to less than T1 or when t equal to greater than T2, this equation may not be applicable. So, okay. So over this period only, the approximation is valid. Otherwise, outside this interval, time interval, the approximation is not valid. Okay. So this is what we have. And error, if I consider the error now, same thing, error here. And during this interval, T1, T2, f of t minus cx of t. Okay. So this is nothing but I can say that f cap of t. So f minus f cap of t. So this is nothing but the error vector. Otherwise, outside that, it is 0. That means you don't know actually. You should not say that it's 0. It is not defined basically. You can say that it is not defined. The definition of this error function or error signal also you can say. And this is valid between the time intervals between T1 and T2. Outside, You don't know basically what is happening outside. You have no information about that. Okay. So for best approximation, what is the best approximation I can do? So what is the size of the signal? Size of the signal means some parameter which says that this signal is a bigger one or this signal is smaller one. So it is not the length. For example, if I take some signal kind of thing, there may be low amplitude signal for long period. There may be some other signal whose amplitude is very large and the duration is very small. So here what matters is, it is not just duration. You should not depend on the duration. This is nothing but your duration. And you should not depend on the amplitude. This is nothing but amplitude. So you should not depend on amplitude, or you should not depend on the duration, because sometimes signals have higher amplitude and longer duration, or higher amplitude and lesser duration. Okay. So ultimately what important for is area under this signal. And I have the negative area here. So to make this positive, what I will do, I square it. So when I take up absolute value, I will get like this. Okay. This is what I have. Something like this. Okay. So this is what, when I project this negative area as a positive area, I can take absolute value, or I can take square also. If I take square, this will become bigger like this. If I take square of this, it will become like this. Okay. These are the squares. These are the squares. These are the only absolutes. The shaded areas are absolute function value. And after squaring, if I do, I will get the bigger area, because to contain the negative area, that is negative polarity, if I square it, automatically polarity will disappear. So I will get the area. So this is nothing but the energy of the signal, basically energy of the signal between T1 and T2. And I can call this as the size of the signal, the quantity of the signal, I can say. So signal is bigger or smaller. How I define? I can comfortably define by seeing its energy. If the signal has more energy, I can say that the size of the signal, the quantity of the signal is high. Otherwise, the quantity is less. Like that, some kind of quantification, parameterization of a signal we are doing. So in the same sense here, I have taken E square. E of T is the error signal, error voltage I should say. And when I square it, it will become energy, because time is involved between T1 and T2. Okay. So this is what is the energy of the error signal, and that is represented by capital E suffix small e. This is after squaring the error voltage, error function, I get this one, and this I can consider as a parameter. This is what I have to minimize. The size of the error signal I have to minimize. That means the energy of the error signal I have to minimize. If the error is less, automatically my approximation is accurate. That is, it is more closer to the original function or original signal. So I should always aim at the approximation which makes the errors energy. Don't say error signal. You should say error signal's energy at the minimum. That is called the best approximation. So best approximation means we should be able to minimize the energy of the error signal. That is what is that minimization? Minimization of EE. This is the notation we are using. Okay. EE is the variable which I have to minimize to get my approximation very close to the original function. So to minimize E, a necessary condition, you know that I have to see what is the parameter here. C is the variable here, because C is an unknown quantity here. See, go back and see here. And if you see here, f of t is the original signal minus C of x of t. Okay, x of t you know, and y of t, f of t you know, but this C quantity, how much part of x is inside the f, that you are not know. This fraction you don't know. So that C quantity is an unknown parameter. If you can solve for this quantity, that is C, you got the solution. So how to solve this one? I have the given parameter. I want to minimize. That means I have to differentiate. I have to differentiate this error quantity, error energy with respect to unknown variable, that is C. So I am substituting for EE here. This is nothing but your EE. So I am substituting this quantity there. Now I am taking square of this one. I am taking square also here. And this I am making it to 0. Okay. If I make this equal to 0, then because it is a traditional thing, if you see the extreme values, finding of the maximum value, min value, finding the min values or maximum values, correct? So this was the thing which we studied in mathematics. So I take this, and here this is in the form of a minus b whole square. A minus b whole square. This is the a square term. This is 2ab term, and this is b square term. All separately you are differentiating. Okay, because it is only summation, so you can differentiate accordingly. Okay, individual terms you can differentiate here. So that again, right hand side equal to 0. Now if I differentiate this, see this term, this f square t doesn't contain c. So it is a constant as far as c is with respect to c. As far as c variable is concerned, it is a constant. So you differentiate some constant with respect to c, you will get 0. So this term is equal to 0 basically. And this term if I differentiate this one with respect to, I am differentiating 2c with c. So I have the 2 here, minus 2 and minus 2. I have here, this is the first term. Okay, this is the first term. Then here c square is there with respect to c, 2c. If I differentiate, I will get 2c. So I am writing 2c here, and this is as it is. This why I am getting this quantity as it is. It is like a constant. It is like a multiplication factor, scalar value, a constant value with respect to c. Don't say that c is a constant. In the approximation, c is the constant, but in this equation, c is the variable. Because we are differentiating the energy, error energy with respect to c. So c is the variable here. All other things are constants with respect to c. So that's why this constant quantity we have to keep as it is, and c square we have to differentiate to get 2c. So this is what we have. By rearranging the terms, I will get c equal to integration t1 t2 f of t into x of t with respect to dt. Integration divided by integration x square of t dt between t1 and t2. So this quantity is nothing but Ex. So what is this quantity? Ex. What is Ex? Energy contained in the signal x. Energy contained in the signal x. Okay. If it is a vector, in case of vector, this we used to call as the length of the vector x. Length of the vector x. Now we don't call it as length of the vector. Length of the vector, size of the vector, quantity of the vector, they are all interchangeably used. Length is specifically used for vectors. When I talk about the size of the signal, mostly we go for the energy of the signal. So this is denominator, same equation earlier, whatever we have done in case of vectors, same equation we got here in terms of functions or in terms of signals. So that is what I have separately written it here. So this is C. This small c, I am writing it here as C12. C12, and first function f, I am writing it as f1 of t. Second function x of t, I am writing it as f2 of t. So here x term again f2, x square means f2 square. So I have modified I have generalized this equation with respect to any number of functions, not only f and x, in terms of f1, in terms of f1, f2, f3, f4, like that, any number of things. So here basically, what is that you are in this new expression, whatever I have given. So f1 of t is the function or signal which I want to approximate. Okay. And in terms of f2, I am approximating. So I am trying to approximate the signal signal f1 in terms of f2. So that is the corresponding coefficient or fraction of the signal to approximate here. So fraction part here. So this is what the generalized equation. Okay. Let us see the graphical evaluation of the component of one signal in the another signal. See here, either I have shown F1. F1 is the signal I want to approximate. Let us say first consider the left side of the left side of the screen. If you see, there are three figures. The first one is F1, second one is F2, third one is F1 into F2. So first one is the given signal. You want to approximate the given signal F1 in terms of F2. In terms of F2, you want to approximate. Okay. So this is the given signal F1. This is the another function in terms of which you want to approximate this signal. So for that, what I have to do? The numerator equation, see here, F1 into F2. First I have to form the product. So I am forming this product. When I form the product, I get here the slowly varying signal or function appears as the envelope here. The fast varying signal is appearing as the another signal inside this. Actual signal is this. Its envelope is modulated with respect to the smallest. Here in this case, this is the slowly varying signal. Okay. So here I have the positive axis. See here, after multiplication, here if you see here, F1, it is a positive signal. This is positive signal. Always positive signal. And here it is a bipolar signal. It has the positive value and negative value. The sine wave. This side it is -1. This side it is +1, let us say. So after you multiply, you have the positive area, negative area. So this area will get cancelled when you add this summation, because integration is there here. You have to find the total area under this curve. So positive area, negative area, approximately they will cancel. These two will get cancelled. These two will get cancelled. Small portion is left over. These two will get cancelled. Like that, ultimately, when I see, I will get very small value. That means, what it means is, very small part of F2. Very small part of F2 is contained in this signal F1. Okay? That means there is no similarity at all between F2 and F1. So F2 is totally different. So this part is almost zero contained in this. This signal F1 contains very, very small fraction of this, or it doesn't contain at all. Okay. So if this C1 if this is equal to 0, if this area under the shaded curve, okay, if the area shaded equal to 0, what it means is product is 0. That means C12, because numerator is 0. Numerator divided by some positive quantity. 0 divided by something is 0. C12 is 0. So C12 means it is a fraction. How much fraction of F2 is contained in F1? So here we should say this F2 is not contained that much in F1, because this C12 is going to be very small value. Maybe 10 to the power of -4. Maybe 10 to the power of -5. So almost 0. This signal is not contained. This signal is not contained in this. That is what is the conclusion we have to make. Now let us consider the right hand side set of signals. Same given signal F1, and this time I want to approximate F1 with another signal F2. What is the difference between this F2, and this F2? What is the difference between these two F2s? There are so many oscillations in the same scale. So this is a high frequency sine wave. This is a low frequency sine wave. Now, when I multiply this, if you see here, so this is the product signal, and as expected, this is the slowly varying signal, not low, slowly varying signal. Basically, it is nothing but low frequency. Slowly varying signal means low frequency. So this given F1 is basically a low frequency signal. So when you multiplied with a high frequency signal, the product was almost 0. Now, when I multiply the low frequency given signal F1t with another low frequency signal F2t, what is happening? Positive area is more, negative area is small. When you subtract this negative area from this positive minus, you have substantial, significant area is positive here. So this numerator is positive value, some positive value more than 0, and it is very significant also. Okay, maybe negative compared to negative area, this positive area may be 3 times more or 4 times more. Okay, so that's why this is a significant value, non-zero value, non-zero positive value, I should say positive value. And that means this low frequency signal F2 is very much contained in this. It is contained in F1 in large quantity. That means there is a great similarity between F1 and F2. This is what is similarity comes into picture. So what you are trying to do in this is, each component you are representing with some function. How much of the signal is contained in the given signal? So it is something like a curry. When you make a curry, what happens? You have to put all ingredients, some pork, and you have to put oil, and you have to put onion, and you have to put some tamarind or afterwards vegetables. Okay, so all these things. But curry is a irreversible process. You cannot, once you make the curry, you cannot get back the ingredients back. Okay, but in our case, in the signal case, if you add so many signals and get a composite signal, an arbitrary signal, at any time you can separate them and any time you can add it. It is a reversible process. Okay, whereas in the real world, when you take the curry example, many of the examples, they are not reversible process, they are irreversible process. Okay, so the signal representation, signal approximation is a reversible process. Okay, compared to our curry problem. So this is what we have. Let us see one example on this. I want to approximate f of t. What is f of t? Given signal is a square wave, and it is one cycle. If I take half cycle, pi means half cycle, 2 pi means full cycle. So half cycle is +1, second half cycle is -1. It is a square wave, single cycle of square wave. It is a single cycle of square wave. I want to approximate with respect to sine of t. That means sine of t, if I plot, this is the sine of t, dotted line is the sine of t, whose frequency is same. Okay, because, in this case, we are assuming like that. We are trying to approximate f of t in terms of sine t. So, whose frequency is same as f of t. That is the reason half sine wave is aligning with half square wave. Okay, half cycle of square wave is aligning with half of the sine wave. Okay, these two are aligned, these two are aligned. Now, when we approximate, what is the error here? So, this is error area, this is error area, this is error area. This is signal minus component. If I take, this is positive area, this is positive area, this is also positive area. Then this is, so this part is, this is negative area, correct? So, two positive areas, positive, and one negative area. This plus this minus this. Now, what is the approximation? Same thing here also. Okay, if you do it for half cycle, that is enough. Same thing is applicable for the next half cycle also, except for the sine. Okay, so let us do this. And I am approximating f of t in terms of sine of t. And I have the fraction part here, c. And I know the definition, c equal to integral t1 t2 f of t into x of t dt divided by ex. This is nothing but energy of the signal, energy of x signal. Okay, x means here sin t is the energy. Okay, now if you see here at the bottom, see x of t is sin of t. Energy in the x is nothing but square. You have to square this term. So squaring is done sin square, and sin square is nothing but 1 minus cos 2t divided by 2. And if you integrate and substitute for this lower limit and upper limit, I will get pi. I will get the pi value for this. Okay, so this pi value I am substituting here. For this 1 by ex, I am substituting here, and this numerator comes as it is. And after proceeding like this with integration, I finally get c as 4 by pi. Okay, so this is nothing but c. 4 by pi. F of t is approximately equal to 4 by pi times sine t. 4 by pi time means, pi means 3.14. 4 by 3, let us say 4 by 3, it is 4 by 3.14. So it is approximately equal to 1.35, 1.36 like that. So 1.36 times, I should say that if I take the given signal, take the second signal, multiply with by 1.36 times or 35 times, you will get the original signal. Of course, you have some error. As I have shown graphically here, there is a positive areas of error, negative areas of error. Okay. But here, you should remember is, I am not interested in the just area positive and directly I cannot subtract. I am taking E square basically. When I take E square, what happens? Energy. So this negative area. Okay. This negative area, why I am calling negative area? This is 1. This is 1. This value is 1. This is more than 1. Let us say 1.2. So 1 minus 1.2 is 0.2. It is negative. So minus 0.2. When I square it, minus 0.2 I will get plus 0.04. Okay. So ultimately, these negative areas are also will go away. Whether it is minus sign or negative, I mean positive sign or negative sign of the error, I am squaring the error function. So automatically positive areas, negative areas, all will become the positive areas only. Then I have to add these things. Okay. So this is one example. For that, I think I will stop it here. Thank you so much for your attention. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.